Hello, my name is Morgan Nix. Today I will be telling you about my OREU summer project, No Pain, No Grain, Standardizing Grain Size Measurement in AM Metals. My sponsor is Texas A&M Summer ORU Program. I would also like to acknowledge my mentors, Cheryl Hawk, Lindsay O'Brien, Nick Gandara, and Amber Black, who are associated with Los Alamos National Laboratory. Here is a little background on who I am. I was born and raised in Houston, Texas. I will be a junior this upcoming fall at LeTourneau University. Also, I am studying biomedical engineering with a minor in mathematics. I chose to study biomedical engineering because although I have a love for math and science, I also love biology and the study behind the human body and its functions. I am starting my core biomedical classes this fall, which will help me determine which area I fit best in and want to continue after college. Currently, the team does not have a good methodology for measuring grain size in additive materials. Current methods are designed for equiax grains. AM material contain columnar grain structures. From the picture shown, the equiax grain structures are more equal in dimensions in all directions, whereas the columnar grain structures are thin and elongated when the metal solidifies. This is an example of a casting. This is representing an ingot, a mass of metal that has been cast into a size and shape. When this structure is solidifying, the heat is moving from the inside out. At the very edge, we can see an equiax grain structure. Moving in from the edge of the mold, we start to see the grain structure change from equiax to columnar. The thermal gradient of the ingot and mold is what defines the size and shape of the grains. In this work, I will be researching ways to find a new methodology that is suited for columnar grains in AM materials. Additive manufacturing is a process of creating an object by building it one layer at a time. The manufacturing process starts with a metal base or build plate. The power source of an electron beam or laser creates a molten pool, which raw material is deposited onto. This manufacturing process creates metal parts. This part is built up layer by layer for the final product. These parts can be used for components in different fields and applied to real-world applications. A grain is a crystallite which forms during the cooling of many materials. Grain size refers to the dimensions of grains or crystals in a metal. We care about grain size in metals because it affects their material properties and their performance. This is true in both additively manufactured and conventionally processed materials. Conventionally processed materials give us an equiax grain structure, and additive gives us a columnar grain structure. My project was focused on additive manufactured materials. AM is difficult because it depends on the direction when the metal solidifies. Columnar grains solidify along the build height, which makes it harder for the columnar grains to be measured. As shown in Figure A, columnar grains are long, thin, coarse grains, and in Figure B, equiax grains are equal in dimension, making it easier for the area to be determined. The standard methodology for measuring average grain size is ASTM E112. These test methods primarily measure metallic materials, but because of their geometric basis, are independent of metal or non-metallic materials. ASTM E112 is best suited for equiax grains. The procedures in ASTM E112 are not great for measuring average grain size in columnar grain structures. Therefore, we are trying to find a technique that works for columnar grains in AM materials. Here are the three standard procedures of ASTM E112 presented in the table below. The comparison procedure performs a visual estimation of the grain size by comparing a live image to a micrograph chart. Grain size estimations need to be made with 3 or more representative areas of each specimen section. The comparison procedure only applies to recrystallized materials with equiax grains, which is why there is a problem with the standard ASTM for defining columnar microstructure in AM materials. The planimetric and intercept methods are always applicable for determining average grain size. However, the comparison charts cannot be used for measurement. The planimetric procedure involves an actual count of the number of grains within a known area. The grains must be inscribed in a circle. The need to mark off all the grains to obtain an accurate count is a downfall to this method because it is more time-consuming than the intercept method. The intercept procedure involves an actual count of the number of grains intercepted by a test line, or the number of grain boundary intersections with the test line. Intercept procedures are recommended particularly from the uniform equiax grain structure. Due to an accurate count that can be made without using lines and boundaries, the intercept method is faster than the planimetric method. We just talked about how ASTM E112 does not work for columnar grain structures, so I decided to look for literature to support my assessments. I read a paper by Pauline Leto called Characterization of Grain Size. Welding is like additive manufacturing. Welding and additive have columnar microstructures. Weld metals have a variety of grain size distributions that can influence different material properties. Leto et al. States that grain size measurement for homogeneous equiax microstructures will not work for columnar grains due to directionality. This is identical to what I found when trying to use ASTM E112 on additive materials. Leto et al. Are averaging the grains width, length, and diagonal of each homogeneous equiax grains. If we were to do this measurement on the columnar grains and measure the length and the width and average them out, it is not representative of the grain. Therefore, this method will not work for columnar grains. In addition, I read a paper by Seth Imhoff called Field Casting Support and Microstructural Feature Examination. Imhoff et al. Found a way to measure columnar grain structures in a cast. A cast generally contains columnar grains in the mold wall. It is hard to measure columnar grains because they are elongated and perpendicular to the mold wall. This method will be shown in the next few slides, and I will show you how it is used in the cast microstructure to measure those grains based on the nucleation sites. Depicted below is an image of the inside of a cast. In solidification of metal alloys during directional solidification, the thermal transport is generally significantly faster than the fusional flow of the solute. The competition between orientation of grains within alloy systems will be more dependent upon the solute transport and grain boundary. The method for measuring columnar grains is called nucleation number density. The grain density is determined by the nucleation reaction. In the figure presented, an example of grain density counting of grains along the cast. Each arrow corresponds to the intersection of unique grains, parallel to the cast. The grains on the edge of the cast are to be counted if it intersects with the cast interface. Over the course of this work, I examined the standard methodology for grain sizing in equiax grains. I found out that these processes do not work well for columnar grain structures in AM materials. I read papers by Leto and Imhoff on characterizing grain size and measuring columnar grain structures. I like the number density method for measuring columnar grains, but I feel like it would be complicated finding the nucleation sites and the grain boundary within the cast. I could see how this is useful for me in my area because a lot of applications of AM are in biomaterials and biomedical devices. In the future, we hope to be able to apply these grain sizing techniques to other metals and materials, examine mechanical properties of grains using the methodology and materials, and collaborate with peers to improve the methodology for grain sizing. First and foremost, I would like to say thank you to the Texas A&M OREU program for giving me this opportunity. I would also like to thank my mentors Cheryl, Nick, Lindsay, and Amber, who are associated with Los Alamos National Laboratory, for being patient and guiding me through this work. This was a great opportunity that I will never forget and hope to apply this material in future endeavors. Thank you.